This is Shakil Ahmed. In this video, we will discuss about generalized additive model. Generalized additive model is a type of statistical model that extends the generalized linear models by allowing a non-linear relationship between the features and the target variables. It consists of two terms. We can say generalized, that use a link function, and we can capture non-linear relationship between the uh, independent variable and dependent variable. And additive means we run individual models, we estimate individual effects, and then for all predictors, and then we add them in a single model to get a final prediction. For example, if y is equal to f1x, then x1, and y is equal to f2x2, y is equal to f3x3, we are running this different single models, and then we get the effects of x on y, where y is basically generalized. Y and x are connected with certain link function, like logistic link function in case of binary, and normal link function in case of linear models, and gamma link function in case of skewed data. So this is just connected with link functions, and we are running individual models and adding up them to get a final model. So it is additive in nature, and it include the smooth function, represent the relationship between each feature and target using smooth function splines. These functions can be captured complex nonlinear patterns like square or cubic relationship between axis and y. And then in final, we just add all the effects of individual effects to get a final prediction. So in this video, we will discuss about uh, again the problem of predicting chronic heart disease based on certain demographic and clinical variables. Uh, we have in Framingham heart disease dataset. I have already uploaded data as Framingham.csv. You can get this dataset from this link from Kaggle. It is available. So we start with pre-processing our data set. We remove the missing values in study variable, in response variable, and we impute the missing values in quantitative predictors by their mean, and the qualitative predictors by their mode. So what we did, first we excluded the drop NS from this variable. This is our response variable. This is available in our data set. So first you can print the missing values, and then you can just run this. You can see there is no missing values, as I have already run the codes before this lecture. So otherwise you could see the uh, missing values in the dataset. But if I run this again, I think then it should be displayed now. Yeah, you can see the missing values in different variables, but we have removed the missing values from the 10-year CHD, so there is no missing values in 10-year CHD. And then we separate the data frame into two sets, one with quantitative variables and one with qualitative columns. So data frame select when data type include float or integer 64. These are quantitative variables, and when the data type is object, it means the data is qualitative, means there are characters. So we just run this, and now you can see we can impute the missing values by their mean when the variable is quantitative, and by their modes when the variables are qualitative. But be careful, if there are a large number of missing values in your data set, then you need to follow certain imputation methods instead of just imputing the means or modes. You need to conduct imputation analysis. You can use machine learning methods based on the available data, and you can predict the missing values. So you can do that. What I did, for column in quantitative columns, we have two sub columns. Then we check, is there any missing values? If there are missing values, then we impute them by a df column, means the selected column, from the selected column, and we find the mean of those which are non-missing. For example, if we have 100 observations and uh, 10 are missing, 10 sets have no data on age, rest of the 90 observation has have data on age, then we can just find the mean of the 90 individuals and replace them by the 10 individuals age. Similarly, for qualitative variable, we did the same thing and replace it by mode. And then we can again see, now you can see there is no missing values in any of the variables selected in this study. Now we extract the x data and y data. X includes all variables, just excluding the response variable, that is 10-year chronic heart disease status, and y consists of the 10-year chronic heart disease status, that is our response variable. So this is a data frame consisting all other variables, and this is a vector consisting only the response variable. And then we need to import the train test split library from model selection, scikit-learn, and we also need pyGAM from logistic GAM, Generalized Additive Models. So from pyGAM we are importing logistic generalized additive model that we are going to use. Basically, we are interested in classifying the data. We have a binary data, so we are going logistic link function. And then this is our uh, trend test split. As in previous videos we did, we just use the trend test split command, and then x data frame, that is a data frame consisting all x columns, and y is a vector of only y, and then we are keeping 20% in test set and rest of the 80% in the training set. And then we are going to build the model, that is logistic GAM, and then fit X train, Y train. These are two inputs. So we just check it. I have already installed it. Otherwise, you may find some error if it's not already not installed. So you need to install it. Uh, any of the package you want to install, you can just write factorial sign pip and then install and then package name. This package we need, this is the library we need to install. So this is already installed, we don't need to install it. I am just skipping this command, and then we have already run this command here, and this is what we need for fitting a generalized additive model. And then we can find the predicted values. I think you can print it. So these are uh, predicted values, and if you want to see this, I think you need to Right, this is in numerical, so you can just print it. It's not still not working. You can just it's just giving the true false values means true means 1 and false means 0. You can just replace it by numbers as well. But for now, we are skipping this. We can just perform the accuracy of the model and then precision and recall. For this, we need to import these libraries from the scikit-learn matrix, import accuracy score, precision score, recall score, and F1 score. And you can also run the confusion matrix as well. So you can just run this. Now the accuracy, it's giving accuracy of around 85% with precision 42% and a recall of around 6.5% and an F1 score of 1.12%. This is giving a little bit higher uh, value of recall and F1 score from the previous ones. And then we can visualize the a partial dependence plot to understand the relationship between each feature and the target. And basically, as we have already discussed in start, the generalized additive model basically runs different individual uh, models of different axes on Y, and then combine all the predictions to get a final prediction. So we will just see how the individual variables are affecting the overall probability of having a chronic heart disease or not. So we can just run these partial dependence plots. So we need 15 plots as we have 15 predictors. So I'm keeping 5 rows and 3 columns there. We are just making a grid. And then figure size 2020. I'm keeping the total size as 2020. If you want to increase, you can increase or decrease accordingly. If you want to, for example, keep this 5 and 20, let's see what happens. We should keep it broader. And then axis, we are basically creating an axis, uh, an empty object where all the axis will be written and saved. And then for I in axis, we have just we are naming a variable axis in enumerate axis. This is number for axis from 1 to, for example, we need how many axes we need. We can just name them. And then for I length of x columns, how many variables we have. We are if we have, for example, 15 variables, and I will vary from 1 to 15. Then xx, this is a variable that from GAM generate x grid and term is equal to I. For all ith term, we get the xx grid. and then it will replicate each plot for every grid. For example, we have 15 grids, then we will get 15 plots. Then we are using the partial dependencies and confidence interval, and that is from GAM partial dependence term I. X is basically the empty vector, and the width of the interval is 95%. We are just making a 95% confidence interval for the uh, partial dependencies. And then axis plot, we have partial dependencies, and then we have confidence interval. This is the color is red, and the uh, type is dash dash. And x set title, basically we are giving title to x-axis, that is x columns. I means it will give the name of every x column, and else it will be the visual, there will be no visualization if I exceed this limit. And then PLT, tight layout means you are keeping all the plots within the layout, and then plot show. So let's see what happened. So these are the plots we need. Now the first one is for male, the second one is for age. So we can see the for female to male. For example, one is male and 0 is female, so we can see there is a higher increase in the coefficient with increase in from female to male. So males has higher risk of getting chronic heart disease than female. Similarly, it's also increasing with age, and almost with no significant uh, change for education. And for cigarette, it's also increasing for some time, and then it start decreasing. I think it should be for this is number of cigarette per day, so it's okay. So it's increasing with increase in number of cigarette per day, and then tend to decrease. So this is basically the change in log of odds, and this is the uh, value of the x variable predictor. So these are all the individual effects. You can see there are different patterns with different variations, and these are smoothed basically for the variables, for the functions we used. And then at last we obtained the confusion matrix using the y test and y prediction. Again we import seaborn, and then again the confusion matrix. Although we missed in above matrices, you could also include here confusion matrix, so you don't need to put again. But for now you can just import the confusion matrix, and then PLT from pyplot, matplot library pyplot, and then find the confusion matrix and then display it on a heat map. So this is the figure size, and then SNS heat map confusion matrix, and then annotation, and the map color is blue, and the title and label and y label, you can see the predicted values versus the actual values. So these are the true negative, these are the true positive, and this is false negative, and this is false positive. So the generalized additive model achieved an accuracy of 85.14 on the data set. The model's performance on the positive class was poor as evidenced by low recall vacancy at 6.5. So that's all about the generalized additive model. This is a good alternative when you are interested in modeling nonlinear relationship, and it's a way of building a additive model ensembling method. So, and you can also capture the nonlinear relationship between the axis and y through polynomial basis functions and other methods. That's all about this lecture. Thank you.